That was. Have you found this z-score for B in the mathematics? 50, which 13 divided by negative 0.61. And then for C, .77. My own, eh? And what do we do with that? Now we are approaching that, eh? We sum these, the total of that is going to be ZX, sum of ZX. Oh, okay, no. Before we do that, once we have done that, then we should do the same for statistics, so that we have two pairs of these scores. A pair of z-scores for mathematics, a pair of z-scores for statistics. So 0.015 times point whatever. Then that plus 0.0161 times point whatever we get. And you do that again. And those multiplications, you sum them. And you divide them by 3. You have the Pearson R. Does it give an idea? So whatever we've done with the mathematics here, you do the same with the statistics, then you come up with those pairs. So that's what that formula is talking about. See, we have done all these mathematics to come up with these z-scores for mathematics. We will have to do the same kind of computations to come up with z-scores for statistics. So the z-score for statistics for student A times z-score for mathematics for student A plus the z-score for mathematics for student B times the z-score for student B for statistics. Similarly here. So those multiplications, when you have multiplied, then you add those and divide by 3, because there are 3 students. You will have the Pearson R. If you go into the statistical books though, they have other formulas which are used to simplify this process. So, but the definition of formula is that. So, so we find using that formula. Should we start a multiplication then they divide or you start with the multiplications. Yeah? So you have a z-score for each student on X and a z-score for each student on Y. You multiply those two. A z-score for student B for X, a z-score for student B for Y, you multiply. A z-score for student C for X, a z-score for student C for Y, multiply. So you would have the multiplication of A, multiplication of B, multiplication of C, yes? You add those answers, okay? And you divide them by 3. That's what it should, well, that's what that formula is talking about. So you start by the multiplications and then the division. That's it. That's a double theorem. Right? Body mass, bomb does. Yeah. Any questions? Now, if there are no questions, then I hope I've answered your concern. At least we have an idea what that formula is talking about. When you get the correlation coefficient after using that formula, the interpretations you make are such that you should never interpret correlation as causation. What I'm saying, you should never say that variable X is causing variable Y. What the correlation coefficient is simply telling you is that variable X is strongly related to variable Y. So the most you can do in interpreting correlation coefficients is to talk about the association, not causation, no. A simple explanation is, if in my area example, if we found that the MCE grades are very strongly associated to GPA, can we say that the MCE grades are causing high GPA? No. What that will be telling you is to say that there is an attribute in the students, an attribute which made the student perform very high at MCE, and that same attribute is making this student perform very high in college. Okay? And of course, I think the attribute will be IQ 8. The student's IQ, this student has a high IQ, and that high IQ made him or made her to achieve very high at MCE. And it is the same IQ making the student perform very high at the university. So, strong association between two variables does not necessarily mean that the two variables are causing each other. When you use the correlation coefficient, it's not a statistical index for measuring causation. It is a statistical index for measuring association. So that first bullet, take note of it. Okay? When two variables are very strongly correlated, that does not mean that changes in one variable are causing changes in another. It only means that changes in one variable are associated with changes in the other variable. Going back to what I've just said there. Any questions on that? Vamvekaire? Mukapanga tuma studies, you do your experiments and you'll be expected to conduct statistical analysis, right? And when you get the statistical indices, you have to explain them. And one of the explanations is this about correlation coefficients, which, by the way, in most research projects, you are forced to assess association. Let's assume that you were conducting a study where you want to test the impact of IGAs on household income. So you'll be looking at the types of IGAs or the amount of money generated from IGAs and the wealth status of these incomes. So you have a variable income generated from IGAs. You have a variable wealth status of the household, whatever way you are measuring the wealth status. In such a study, you'll be expected to correlate the two variables to be able to say, yes, if you have a good IGA, you are going to be improving the wealth status of that household. If you have a poor IGA, if you don't have an IGA, the wealth status of that household will be poor. You will do the same in a study where you are saying, what is the impact of IGAs on food security? What is the impact of child nutrition on achievement in primary school? So you'll be looking at grades in primary school versus levels of what? Nutrition. You have to correlate and be able to say, if you feed your child very well, he or she is going to perform high at the university. So correlation coefficient is a very useful statistical technique, which we are likely to use in order to describe our populations. But when you are doing that, pay attention to this. The other aspect I would like you to take note is that when you are interpreting a correlation coefficient, remember that that coefficient is in part a function of the variability of the two distributions and in part the association of those two distributions. Because of what is it? Going back to Conwan's graph, let's make it positive now. Let's assume we had a distribution two distributions showing this kind of association. How would you roughly describe the association in this case? Are the two variables associated? No. Yes. Huh? Yeah. No. I would say they are associated, but the association is what? Weak. It's going towards a zero relationship. Now, what we are saying in that bullet is that if they are related, it means that when you change this variable must change. So changes in this variable are influencing changes in this variable. Wait. But that's not the only story happening in this. There are other variables influencing changes in this variable. There are other variables influencing changes in this variable. The fact that maths is associated with statistics is not the whole story. There are other things happening. And those other things could be, for example, I am a teacher in mathematics. She is a teacher in statistics. Would our abilities to teach be the same? They would be different. So I would be bringing in variability because of the way I'm teaching mathematics. She will also be bringing in variability in statistics because of the way she is teaching statistics. So apart from the association that maths and statistics have, there are other associations occurring, and those associations are the ones which are explaining this behavior. Okay? So, when you are interpreting your correlation coefficient, remember that that is happening. Okay? So, you'll be talking about the association between maths and statistics, but you have not included the influence of teaching ability. It may be that mathematics is being taught in this classroom, statistics is being taught in upstairs, and the way the room upstairs is fresh is different from this one, because this one, the windows on one side are very high. That one, the windows from both sides are on the same level, so there's a lot of air circulation. Students are fresh, the lecturers are fresh, so they are teaching much better than when they are in this other room. All those are factors which will influence variability. Okay? Thus, in contrast to where you have that all the scores are falling on that line, it means that the variability happening in maths alone is very little, and the variability happening in statistics alone is very little. The largest variability which is occurring is that of the association between the two variables. Okay? That's what I'm saying in bullet number 1. Questions before I go to bullet number 2, because those bullets are very loaded. That's why I'm explaining each one slowly. The other caution I would make to you is that if you are planning to conduct a correlation study, you should be very careful on the methods of sampling you will use. Because if you don't do proper sampling, you may end up restricting the range of your correlation coefficient. Let's assume, in this case, the association we have is very strong, but it's not perfect. Like Gondwan's association was. If you plotted a scattergram and it showed you that, how would you describe it? That would be saying there's a very strong association in it, but it's not perfect. Those people who are low performers in mathematics are also low performers in statistics. Those who are average performers in mathematics are also average performers in statistics. Those who are high performers in mathematics are also high performers in statistics. Let's say that's the population. And you wanted to come up with a sample to conduct your study. And in your sampling method, you only ended up sampling those students. Now let's plot a scattergram or a scatter plot for those. How will it look like? Is it not going to be a scattergram? It will be, which will be showing no relationship. But actually, there is a relationship. The problem is you have just sampled from a restricted range of that population. Okay? So when you are conducting correlation studies, you have to pay attention to what sort of sampling technique you are going to use and what sample size you should use. If you use a larger sample size, the possibility is that as you're increasing the sample size, you are going to be including these students on the other side, and it will give you an idea, a better idea of the correlation coefficient. But the smaller the sample size, the most likely you will restrict the correlation coefficient. It will also happen in the same manner if you did it here and you plot that, it will still be her graph. Okay? You could also end up sampling, and you just sample those who are falling there, and you end up seeing very strong relationship, but you have left out these who are falling off the main line. So restricting the range of your correlation. Okay? So you have to be careful when you are sampling for studies that are going to involve correlation procedures. I think we can justifiably stop there since we didn't break. I can see people, we have talked a lot. Next time, next week, on a Monday, we are meeting educational statistics here. The introduction to applied statistics will be elsewhere on Wednesday at 1. Because once we finish this topic, now we are going to be talking things which are different. So I'll finish my discussion in a separate group, and then the applied statistics will continue a little bit to talk about the inferential statistics, whilst the educational statistics will change direction to start talking about measurement. Otherwise, nice week. Yes. Not going through the whole thing, but if you have areas where you're not sure of and you have questions, literature. Oh, what questions? Okay, send me just the problem statement, the objectives, and then the table you are talking about. I'll respond. Yeah. Anyway, you can just send me the whole proposal. I'll just pick what I need to look at.